Okay, guys, let's continue. Let's continue and Slava. All right, so let's begin our uh, last lecture of Chong.
All right, thanks for coming. Thanks for making it all the way till Friday. So today, the first part, I want to do two things. So the first part, I want to finish up what I wanted to say about the deconfined criticality. So the more practical side. Essentially, the somewhat funny or amusing situation with Monte Carlo, Bootstrap, and a possible complex fixed point. Okay. So I want, hopefully, we can make this lecture or talk a little bit different than the previous couple of days, because quite a few of the major players on this topic are sitting in this room. So, we could have totally make this more like a discussion session. So feel free to just interrupt and comment at any stage. Okay. So, so I've been talking about DQCP, pretending that it's a nice, good CFT, but in reality, of course, things are complicated, and eventually, whether this strongly coupled fixed point exists or not has to be decided by numerical calculations, one way or the other. Okay? So there has been a lot of Monte Carlo works done on this problem since the 2000s. That's almost 2 decades. Anders was a pioneer in on this regard. So a lot of people contributed, like Anders and Ribu, who's a remote organizer of this workshop, Adam Nahum, and many others. Okay. And people worked really hard to go to a pretty large system size. So the typical size one goes to is of order 100. You can go to several hundred, depending on exactly what you do. But as Anders commented yesterday, you don't necessarily want to compare apple with pear. So they are slightly different models. So 200, 500. But the maximum one goes to is of order 500. So pretty big by any standard. So the conclusion was, there are several conclusions. One is there's no obvious sign of first order transition, at least for a lot of these models. Right? And of course, you can always twinkle the model enough so that it becomes a first order, because first order is, for any transition between any two phases in a clean system, first order transition is always an option. But at least this model, without any apparent fine-tuning, do not behave as first order transitions. And then there's this emergent SO5, or in the easy plane case, O4 symmetry. That's widely observed in pretty much all these models. If you measure correlation functions, it's roughly power law. Okay, so it all looks pretty good, pretty much like a continuous transition, except for two things. So the first point is that if you try to extract critical exponents, as I said, things looks like power law, so you can extract some critical exponents out of it. But they keep changing as you vary system size. They keep drifting. Drifting just means changing slowly. Slow enough that for a small range of system size, it looks like you can still extract a reasonable, some reasonable exponents. So typically, the measured scaling dimension of the corresponding operators goes down. Typically, drifts down as the size goes up. Okay, even up to the maximal system size, which is usually considered pretty large. And the second thing, which by now is pretty widely known, is that the extracted scaling dimensions on, let's say, the largest system size do not agree with what numerical bootstrap has obtained. In particular, they are always smaller than the upper bounds. Sorry, the lower bounds. From numerical bootstrap. In fact, I won't even bother quoting the actual number because the bounds from the numerical bootstrap is not a tight one. It can be even further improved if one wishes. So at least that's what I was told from the experts. Right? This, together with the fact that when you go to a system size larger, typically the scaling dimension goes down, means that it's probably hard to resolve this issue by hoping that things can take care of itself by going to even larger system size. Right. So if you want to check out more details about exactly what the bootstrap says, you can always look at the review. I think two of the authors of this review is here, so okay. So basically the upshot is that if you look at these two aspects, it doesn't quite look like a continuous transition, right? But it's certainly not an ordinary first order transition. For that to be the case, if it's a first order transition, what we know is that it's certainly very weak. Right? The correlation length is at least larger than this number, so you have a correlation length of order 1,000. And normally when you see that for an ordinary first order transition, it just means your lattice model is terribly fine-tuned. It just happens to be, you happen to be very lucky or unlucky, depending on your viewpoint. But since this kind of thing has been observed for a quite wide range of models, by now there are like easily 4, maybe even more different type of lattice models. Not every model has went up to size as large as this. I think there are only 2 lattice models, the one by Anders, the one by Adam Nahun, that went to order 100 system size. The other ones, some of them require microscopic fermions to realize, so they go to smaller size. But still, people see more or less consistent results. So it seems unlikely that all these models just happen to be terribly fine-tuned. Right? So then the question is, if it's a first order, if it's not terribly fine-tuned, how do you get such a large correlation length? Right? So a possible resolution is that well, there is a fixed point, right? So for ordinary first order transition, there's probably not even a fixed point or nothing close. But there is a fixed point, but it's not a real fixed point. It's a slightly complex one. Right. So it's not a unitary fixed point, which means for the actual quantum lattice system, you never hit this complex fixed point, but you can get very close to it. Right. So let me just illustrate to you roughly how it works. I won't go into too much detail, but so let me just explain the idea with a cartoonish RG flow equation. Okay. So imagine you have some coupling constant. You know, this could be your quartic couplings in the critical gauge theory, for example. Some coupling constant lambda, and under RG, the beta function looks something like this. So L is your RG scale, lambda is your coupling constant, and this epsilon is a constant that doesn't flow under RG. Right, so if you imagine changing some of the parameters in your theory, this epsilon could be something like I don't know, your space-time dimension, maybe minus some critical dimension, or it could be your the flavor number, which I mentioned yesterday, but maybe the difference between your flavor number to the critical flavor number could be various things, right? For example, in 2D pulse model, this could be proportional to Q minus 4, where Q is the Q state pulse model. So it's some constant that defines your theory but doesn't flow under RG. So that's the idea. Okay. Of course, you can have higher order contribution, but the assumption is, for now, let's assume epsilon is small and lambda is small. Okay. I mean, in reality, it can, of course, be more complicated, but this simple scenario is enough to show the idea. Now, let's just examine what happens with slightly negative and slightly positive epsilon. So if epsilon is negative, you have a more standard scenario. Let's say you have lambda, you'll have two fixed points at so fixed points at lambda star equal to plus minus square root epsilon. Sorry, square root absolute value epsilon. And then one of them is attractive, the other one is repulsive. Okay. Pretty standard stuff. The funnier thing is what happens when epsilon is positive. You have no fixed point on the real line. Your RG flow is monotonic. Of course, if you really solve for fixed point, you get fixed points that are slightly imaginary. you get this. So of course, if your theory starts on the real line, it flows always on it keeps on the real line, and you never actually hit the two fixed points. But the RG flow can be very slow when you are near this fixed point, right? So to see how slow your RG flow goes, you can just calculate the correlation length, right? Essentially, just integrate this beta function. This is a fairly simple integration to do. Sorry. So RG. So the typical correlation length, right, which you get, the log of the correlation length is the difference of the little l, and that's given by the integration of the beta function from some minus value, some minus lambda to plus lambda 0. Let's say it goes from some negative value to some generic positive value. Exactly what this value is doesn't matter because this integral converges on the entire real line. So you get something that looks like pi over square root epsilon, which means your correlation length is exponentially large in this 1 over square root epsilon. Okay, so the flow can be, putting some reasonably small epsilon, like, I don't know, 0.1 or something, you already get a pretty large size. Okay. So you get a very slow RG flow for lambda within the range of the square root epsilon. Okay. So if your RG flow is slow, it just means that you spend a lot of RG time, aka length scale, near this complex fixed points. Right? So the physics below that length scale is still controlled by those fixed points, even though you never reach them. Right? So below that scale, you can essentially still talk about everything we like to talk about critical points. We can talk about scaling. We can talk about almost power law correlation functions. We can talk about whether a perturbation is relevant or irrelevant. We can talk about emergent symmetries, because the symmetry breaking perturbations will be irrelevant, as long as your system size stays below that energy scale. Okay. So there's some known examples where this happens. With pretty large correlation length. By the way, when I say correlation length is that number, that's kind of the most natural correlation length without much fine-tuning, right? That is assuming that I start microscopically from some generic point here and flow to some other strong coupling regime here, right? You could have started from here, in which you'll get a strong first-order transition, right? Because your RG flow will be very quick, very fast. But the point is, this entire region will more or less have that correlation length, so you don't need fine-tuning. All right, so some known examples. As I mentioned, the 2D classical Q-state Potts model. So the epsilon will be proportional to Q minus 4. And for Q equal to 5, the correlation length is roughly of order 3,000. And the theory explaining all this was recently developed. If you want to check out the details in this paper. Okay. And since then, people have found weirder and weirder examples. For example, there are this 1 plus 1D analog of DQCP. With Z3 cross Z3 symmetry. I think it's basically a phase transition between one phase where you spontaneously break one of the Z3 and the other phase where you break the other Z3. That one, at some generic but happen to be solvable point, the correlation length is of order 10 to the 5. The reference is this one. Right. This is not a number that you ever reach with any lattice simulation, but it just happened to exist. Right. So this kind of thing definitely exists, right? And in fact, if you look around, they're not that uncommon. So this kind of phenomenon, by the way, if you look at the literature, there are multiple names given to it. So this slow RG flow, due to essentially this mechanism, it's sometimes called the walking coupling constant. Well, as opposed to running coupling. Sometimes it's called the conformality lost. Sometimes it's called pseudo-critical. Okay. And the current understanding, well, the current thinking at least, is that perhaps for the deconfined critical point, the most likely scenario is something like that, right? Yes. Right.
A question?
Yes.
So if this is the, are you saying that there should be a lattice implementation where you can see the strong first order, or?
Oh yeah.
And we have been unlucky so far?
Yeah. In this scenario, as long as you push your UV coupling to this side, it's a strong first order.
So there should be one implementation where you see this.
Oh, yeah.
But we have been unlucky so far?
Sorry?
And people have been unlucky so far?
No. The thing is, even if you have a true critical point, you can always play with your lattice Hamiltonian to go to a first order transition. I mean, in practice, it may or may not be easy to find such a perturbation, right? So if you just find a very different Hamiltonian that is a strong first order transition, that may not mean much. But if you somehow have some continuous tuning, and then if you can observe how it crosses over from this weird, more or less critical behavior to a strong first order transition with everything in between sorted out, that may mean a lot. Right? I think that's what Anders tries to do in some.
That's what we can do. I may be able to tell you something about that later.
Yeah.
A question.
Yes.
So, is the conformal bootstrap finding an island yet?
No. The thing is that Bootstrap didn't find anything like this. It gives some bounds, right? It gives some bounds saying below the bounds there's no unitary CFT with all these nice properties I was talking about, and all the numerical findings are well below that bound.
So, if the bootstrap eventually does say that maybe there is a CFT.
No, the thing is, it's. I mean, unless they actually find a tiny island, Otherwise, the bootstrap only tells you what's not allowed.
Right.
Right. So far for with this constraints, I don't think an island has been found. I mean, with SO5, of course, you can find an island, but that's probably just Wilson Fisher. Anyway, so yeah.
And is it also a possibility that there is a second order phase transition, nice fixed point, but it's just not conformally invariant?
Yeah, we pondered about that. That's actually a, depending on your viewpoint, crazier, more entertaining, probably more interesting scenario, because in 3D there is no proof that with Lorentz symmetry plus scaling invariance necessarily is conformal. In fact, the 3D free photon is an example. But I think the belief, someone can correct me if I'm wrong, the belief is that only appears for free theory. At least we don't know any example of interacting theory that's of that sort. But it's not, there's no, as far as I can tell, there's no proof. No, the Maxwell theory, yeah. Yeah, so, we ponder through various funny possibilities throughout, but this seems to be the least dramatic one. So, yeah.
Is there any other kind of mechanism give you a correspondence?
Sorry, I can say it again?
Is there other mechanism that can give you a weakly first order transition?
Of course, the other mechanism is you just happen to be fine-tuned.
Fine-tune, okay.
Right? That's always, it's, I'm not sure if it can ever be rigorously ruled out, but it just feels, you have to be very lucky there, especially given you have multiple lattice realizations. Right? But admittedly, when I say there are 4 or 5, except for 2 of them, all the others are at this point are still on pretty small system size, because they all require fermions, so they go to something like 20 by 20 or something. That's pretty much it. So 20 by 20, you get some exponents. Of course, you can always question how much do you want to trust that. Yeah. But they are roughly consistent with the results from larger system size.
So other signature that can distinguish two scenarios is fine-tuning versus pseudo-criticality.
Yeah, I think if you want to rule out fine-tuning, you just try a few different models. That's,
I see.
Yeah. Also, if it's well, okay. Even if it's fine-tuned, there's the difference between having, okay, even the fine-tuning situation, there are roughly 2 subcategories. One is there is no fixed point, or there's only some extremely trivial fixed point, and you are just fine-tuning around there. The one example I can think of is the 4D abelian Higgs theory. So that one is first order, but it can be made arbitrarily weak if you tune the UV Maxwell coupling arbitrarily weak. And there's no real fixed point there, unless, except for the absolutely trivial free theory. But then, of course, you can also imagine a situation where you happen to be near some other, probably even funnier critical point, and then you may happen to be close to there. But that requires more exploration of the lattice model and all that. Yeah.
This fine-tuning issue, so it has to be a singlet operator, right? The second singlet operator.
Yes, yes.
And by looking at the model, the microscopic model, do we have candidates of the field theory? Do you imagine that?
No, you can add things like higher, like next neighbor coupling or higher spin meaning involving more than just 2 or 4 and so on. I think that's part of what Wenders tries.
People who believe in the fine-tuning scenario, I think what they should do, if they believe that they have some fine-tuning, okay, they can use this fine-tuning to remove the drift in the critical exponent
that's probably true.
And to measure like the good response is not great, they could measure also the dimensional separator, which is fine-tuning.
Yeah.
And then bootstrap people can redo the bounds and see if it's consistent or not.
Yeah, I
Because even if the theory is fine-tuned, it's not guaranteed that it's going to be consistent with the bootstrap bound.
true, because there is this thing whether you are fine tuning near some actually interesting fixed point or just some really boring scenario, right? So it's even if it's fine tuned, that issue has to is there. Yeah, I don't think up till now. Maybe Anders will comment more later. Anyone tried to very seriously try to tune the additional operators to see. It's probably some computationally very costly thing to do anyway.
Well, I mean, we definitely do that numerically. I mean, that's not yet published, but that's what we're working on.
Yeah.
I may say some of that.
Yeah. All right. So yeah. Any other questions, comment? Yeah. Okay. So we just say it's probably of this type. So I said the correlation length is probably at least 1,000 or something. At least that seems to be reasonably generic, but we'll see. So some theories on this, which I won't go into detail, or I won't go into at all, but just in case, if you want to check out more about this possibility, specifically for the DQCP, I think there's a very early paper from Alan Hu talking about this from the point of view of abelian Higgs theory. Then there are two slightly more recent ones talking about this from the point of view of Weisselmino-Witten nonlinear sigma models. Anyway, just in case you are curious, I won't go into them. And that's probably also the case for the easy plane, even though the easy plane seems to, it seems to be more obvious that the transition is first order. The correlation length is somewhat long, but not long enough to be inaccessible from numerics. It's probably something of order 100. But the dust has not, I say, fully settled. The easy plane DQCP is supposed to be dual to QED3. So easy plane CP1, that's supposed to be dual to QED3 at NF equal to 2. So this has been done quite seriously in the lattice gauge theory community, and they haven't seen anything that looks like this walking coupling scenario. But it may be understandable there because in their calculation they have to take the continuum limit quite carefully, so push the lattice UV coupling to weak coupling first before you start RG flow. That already gives you some cost in terms of system size. So so they may not be seeing the very large correlation length at this point. Yes? Say your last sentence. Yeah, that's the question, right? So it looks like from because the easy plane DQCP is having similar issues, so it looks like it should not. But an honest lattice simulation at this point seems to have not seen that. It looks conformal. In fact, if you when they extract the scaling dimensions, it agrees reasonably well, or surprisingly well, with large n, for a reason we don't understand. So, yeah. No, bootstrap on QED is QED3 is a delicate subject. I think it's something that people are still working very hard in progress. Yeah. I mean, the thing is, they can rule out certain exponents. They will say these exponents don't make sense. So from that point of view, probably is ruled out. I think the experimental data do not, the Monte Carlo data do not agree. Okay. So one last comment is that even though things are eventually probably first order, practically this can still be as interesting as a real critical point, because now you say, okay, if it's classical system, you say, okay, your real system size is probably always larger. Even though if you get something like this, if you look at it, it's already in the micrometer range, which is pretty crazy. But if I think about quantum phase transition, there is a scale which is always finite, which is temperature. And you've probably seen this famous critical find. If I have some tuning parameter across some critical point, then there is an entire region at finite temperature that behaves like a that has critical scaling and all that. So this, let's say, suppose you have some UV energy scale, let's call it J. So this walking coupling scenario is telling you that until you hit some very low temperature, something of the order J over C, let's say, that's like your microscopic scale divided by 1,000 or something, which can be pretty small. For condensed matter system, this is something like several hundred Kelvin, so typically. So until you hit here, where things may become less critical, this entire fan is still there. So you can still talk about those critical scaling and all that. So yeah. So yes.
I'm just a bit confused about making sure what you're saying. So in the disk in the bottom, it is not critical.
Yes.
But then it becomes critical?
If you look at the temperature above this, well above this scale, but well below the microscopic scale, it looks as critical as typically what you see in critical fan. Okay. Yeah. Is there another question? Yeah.
Is there any solid state experiment where people think there might be a DQCP?
I mean, depending on how you define it, one thing you can say is that even though it's not conformal, the Kohn-Luttinger instability is kind of like that. So that's kind of in fact, the Kohn-Luttinger, I think it flows even slower than this one. Let's say you start from repulsive interaction for a circular Fermi surface, right?
Yeah, but is that observed in anything? Helium-3.
Yeah, helium-3, whether it counts or not, depending on how you view it, I think.
Are you saying helium-3 has a deconfined quantum critical point?
No. This walking coupling scenario is much more, can be much more general than DQCP. Are you asking whether there are solid state realization of this walking coupling constant or the DQCP? DQCP. Not yet, unless Anders want to comment on.
Maybe I will talk about this during the conference week, but I mentioned this material in my introductory talk on strontium kappa borate, and in fact there are recent NMR experiments under high pressure and magnetic field, which seems to see something that fits well into this scenario of equal quantum criticality. In particular, this quantum critical fan that Chong mentioned there is somehow seen. There's some finite temperature scaling seen. There's a paper online already on that.
Yeah, so we'll see. Yeah.
We'll see.
Sir, I saw another. Yeah, Wei Chen, were you asking something?
I just want to kind of thing looks very much like superconducting dome. So in the superconducting dome,
I deliberately draw it like that. Yeah.
Yeah, in the superconducting dome, in the experiments, do we see such kind of walking behavior, like scaling dimension will increase with the size increases?
No. Yeah, there is very. Well, okay. First of all, it cannot be a CFT there, right? But that much is clear.
But
The exponents measured seem to be extremely robust, at least for cuprate. Maybe for some other material, it's less so. For cuprate, I mean, it looks like cuprate, but probably the belief, or I mean, at least it seems reasonable to say that even if you remove the superconductivity, those funny behaviors are still there. I mean, which is kind of what people do with strong magnetic field. They can suppress superconductivity to a large extent, and many of the strange metal behavior are still there. Also, for example, if you look at the linear T behavior, the slope, that slope is just a straight line all the way from the lowest to, I don't know, melting point or something. So yeah, it doesn't seem to, nothing seems to drift there. It's, yeah.
Okay.
All right, so I think with that, I guess we can take a break for now, and then. All right. Okay. The final topic I want to mention quite briefly is the story of Dirac spin liquid. So up till now, I've been basically just talking about critical gauge theories with one flavor and two flavor. Here's a story that's equally exciting, probably to me even more exciting, with four flavors. Part of the excitement is because it's probably actually there, but we'll see. So I want to talk about QED3 at NF equal to 4. So remember the easy plane DQCP, that's dual to two flavor. So now I have four flavor. Just from the field theory point of view, this is probably a better hope for conformality. Right, just because, well, we know if NF is large enough, you're definitely conformal. So this probably has a better hope than NF equal to 2. So the current numerics, I won't go into much detail. I'll just say that they're encouraging. I'll come back. I'll come to that soon. Yeah. But so far, the numerics is encouraging, but it has not received as much scrutiny as the deconfined critical point. So we'll be cautiously optimistic to be scrutinized. Right, you can either try larger size numerics, which has some challenge, I can mention later, or bootstrap. And as I mentioned, bootstrap for QED3 is an ongoing effort, as far as I understand. Sorry, let me just write down the Lagrangian for you. It's just of the two-component Dirac fermion coupled to a dynamical U1 gauge field. Remember the way I regularize things, there's a level 2 Chern-Simons term. But if you look at the more commonly seen way of regularization, it's very often just written without the Chern-Simons term. Important thing is either, it doesn't matter which way you regularize it, just the important thing here is that it's time reversal symmetric. Okay.
And is it also parity invariant?
Sorry?
Is it also parity preserving?
Yeah, parity is there. Yeah. So why does it call Dirac spin liquid? Well, the original proposal was that it appears in it can appear in spin systems. It can emerge out of some frustrated magnets, and I think that hope has more or less finally been fulfilled over the past several years, I think there are emergent, more and more numerical evidence emerging that this funny guy is actually there. So specifically, it's there on the triangle lattice. If I think about a triangle lattice magnet, anyway, let me just, what I've been doing, right? And I put a spin half moment per site, right? So on each site, I have a spin half. Let's say you have the 4SO3 symmetry and the symmetry of the lattice, of the triangle lattice. So you can write down some antiferromagnetic Hamiltonians. The simplest Hamiltonian you can write down, of course, is just the nearest neighbor coupling, right? So, so here, nearest neighbor just means this one is your J1, right? In fact, this is the very model that inspired Anderson to propose the whole idea of spin liquid and resonating valence bond solid. So Anderson was hoping that this could give you a quantum disordered ground state. It turns out that's not true. That doesn't work. Turns out what happens with this theory is that the spin still order with spin half moment, it orders in this famous 120-degree type of pattern. Right. It does something like this. So on the triangle, if you go around each triangle, the spin rotates by a full circle. Right. So that's what happens with only J1. It turns out if you add a little bit of J2, which is the second neighbor coupling, so this gives you J2, but just Heisenberg interaction. Okay, and then you vary this ratio between J2 and J1. Then it's found that with a little bit of J2 turned on, I think 0.1 something, I don't remember the number, this 120-degree magnetic order is destroyed. You go to some funny quantum disordered phase that looks very much like a spin liquid. And
Can you define what do you mean by spin liquid?
yes. In the context of this lattice system, it is a ground state that's not magnetically ordered, and also it is a ground state that preserves the 4SO3 cross lattice symmetry. But of course, that's for this state. But in the more general setting, the definition of a spin liquid is that you have a spin system and the ground state is what's called long-range entangled, in the sense that it's either gapless, critical, or has some topological order or underlying TQFT description. Like the toric code will be an example. Yeah, so something that doesn't admit a local order parameter description. Yeah. And this Dirac spin liquid is one type of spin liquid. So there's a critical value here. And then if you further crank up J2, yes?
Can you define what is Dirac spin liquid without reference to this Lagrangians, or Dirac spin liquid definitely refers to this Lagrangian?
Yeah, so it's the cleanest definition is just that this phase has the same IR behavior as the IR of that Lagrangian. Yeah, because that's a well-defined continuum field theory, so the IR is unique, I mean, whatever it is. So, yeah. Well, actually, okay, let me qualify. Assuming that's actually conformal, or it doesn't flow to some relatively boring spontaneous symmetry breaking phase.
If you change the number of flavors from 4 to 8, say, is it still Dirac spin liquid?
It is. It's it just this flavor number happens to be more natural for this specific setting. For example, if I change my SO3 symmetry to some PSUN or then you can have more flavors. Yeah. Yeah. So that specific form and flavor number is picked just mainly because it seems to be there. Yeah. So if J2 is large enough, you have some okay, this is called the 120-degree order. And for larger J2, it's something called stripe order. This is less interesting. I won't say too much about it, but you know, it's some other form of magnetic order which looks like this. This transition seems to be first order, so there's probably not too much to say about it. But the interesting part is over the past several years, people have accumulated more and more numerical evidence suggesting that this is described by that Lagrangian. Right. So it looks like a critical spin liquid in the sense that correlation, it's a finite region, it looks like a stable phase, and it looks gapless. The correlation function is probably algebraically decaying. Even though the current numerics, the system size is so small that we can't quite extract a reasonable exponent yet.
But previously, people were saying that Kagome lattice was the leading candidate. Can you comment on how this compares to Kagome?
Yeah, the Kagame is probably another candidate where, okay, different people may have different opinion about this, but I would say our confidence on this one is probably stronger for two reasons. One reason is for this one, there, especially this year, there has been even more numerical supports from various other methods of calculating. For Kagame, if you look at the numerics, I think the data is less clean, but different people may think differently. The other thing is, even from a theory point of view, the triangle lattice has a better hope of being stable. For one reason is that if you ask what are the relevant, what are the perturbations, probably relevant, what are the perturbations allowed by these symmetries, this SO3 and lattice. On the triangle lattice, it turns out you can add something like, schematically, a monopole operator, but that carries 6 pi flux. So it's something like a 3-fold monopole. So from all the evidence we have, this should be an irrelevant operator. On the Kagame, the corresponding operator is a 4 pi monopole. That's symmetry allowed, so it's there on the Kagame. We don't know if it's relevant or not. Large N give you something like 2.5 something, right? So there's hope that it may be actually irrelevant, but we don't know, right? In fact, this is a key. This is the critical number that we really very much hope to get from either Monte Carlo or Bootstrap. It's not there yet. Yeah, another reason is on triangle, it turns out there is a prediction from theory that's easier to see numerically. That's not as simple on Kagame. Okay. So this is probably QED 3 and F 4. But again, the issue of conformality is still there because we don't know if you go to system size 1,000 by 1,000, if it's still there. Nobody knows at this point. I should also comment that there is a material. Yeah, I forgot to look up the exact compound: sodium, magnesium, something. that shows some sign that's consistent with this behavior, but it's less. Let me just say it's even less clear there. Okay. So the goal of this lecture, I mean, the full story is a bit complicated one, so I'm not going to go from square root 1 and show you how the theory works. So just to give you a flavor of how things work, let me just talk about one relatively simple aspect of this theory. Let me explain why this Dirac spin liquid is a natural thing that appears near the 120-degree magnetic order. Right? So previously on the square lattice, right, the natural antiferromagnetic order is this collinear nail and up down, and there I sort of explained that a natural critical theory or a critical gauge theory that can emerge out of that is the DQCP, it's the CP1 gauge theory. But turns out on the triangle lattice with this non-coplanar 120-degree magnetic order, the analogous critical gauge theory that can naturally appear is this NF equal to 4 QED. Okay, so that's what I hope I can show you today. So show this coplanar magnetic order out of QED 3 at NF equal to 4. So there are a lot of details that I won't go into, but if you want to learn more, it's this reference. Okay. So the starting point is that, let me first explain one more thing, which is the reason why, so sometimes, sorry. I should explain one more thing, which is the definition of that Dirac fermion, especially the fact that it transforms as a spin-half object under the spin SO3 rotation symmetry. This is very similar to what you see in the CP1 model. The gauge charge carries spin-half. In fact, that's required by what's called the Lipschitz-Martis theorem on the lattice, but let's not go there. So essentially, the 4 flavors, you can organize that into two component flavors, and one of the component will be the spin. So this alpha is up or down, that's the spin, and this guy forms a spinner under the SO3. This V, sometimes called the valley index, let's just denote it left and right. It's basically where they appear in the Brillouin zone, what lattice momentum they carry. Let's say this is R, this is L. So it's just 2 different lattice momentum. But I won't actually use any information about that. Just telling you that it's some label. Yes.
Is the spin Lorentz spin?
No. Yes. This spin is this spin. It's SO3 symmetry here. Yeah. Yeah, I'm suppressing the Lorentz index entirely. So yeah. So the fact that this guy transforms as a spin half is the reason why this is sometimes called spin-on. All right, so now we have enough information to show you that this QED3 is naturally in proximity to some coplanar magnetic order. So now one thing you can analyze, very similar to what we did for the NF equal to 2 QED, is to think about the monopole operator. Right. So I have, again, a monopole operator for the M, but then that Chen-Simon term at level 2 is telling me that I should compensate the extra gauge charge from the Chen-Simon term with 2 gauge charge. So I should attach 2 fermions to it with some index here, alpha 1, V1, alpha 2, V2. Of course, they are fermions, so these 2 index should be anti-symmetrized. So again, it's helpful to think in terms of the state operator correspondence. So let's just do state operator correspondence. So again, let's put the state, the theory on S2 space, and with a flux background. Of course, things are, as usual, safer in large N limit, but this kinematic aspect, we expect it to be there, even down to NF equal to 4. Okay. And with fermion, the saddle point will be even simpler than with boson, because there you just look at how the fermion modes behave and fill up all the negative 0 modes, right? So the energy level for fermion will look like a bunch of Landau levels, essentially. So these are 0 energy, and there will be some negative energy modes, which for ground state, you just fill it, and for positive energy mode, for ground state, you leave it empty. And this structure of 0 mode filling is just telling you that the gauge invariant monopole should have 2 out of the 4 0 modes filled. Remember, each Dirac fermion gives you a 0 mode. So there are 4 flavors, so in total you have 4 0 modes, and this is telling you that 4 out of the 2 0 modes are filled. Right. Sorry?
2 out of the 4.
Yes, 2 out of the 4. So gauge invariance there are this number with 6 monopoles. And there's a good reason why it's 6. It's because since I have 4 flavors, there's a natural SU4 flavor symmetry. So this monopoles, this guy, forms a vector, forms a 6-dimensional representation of SU4. And the thing is, SU4 is basically SO6. So if you mod by Z2, it's SO6. So it's basically a vector under SO6. All right? So that's some basic facts about the monopoles. I think, yeah, okay, this one. So now let's try to get a magnet out of this QED3. Let's try to have some spontaneous breaking of the spin rotation symmetry. Well, the way to do that here is essentially you add some Landau symmetry breaking theory on top of this QED3. Right? So let's add a bunch of things. Let's add a 3-component vector field. Let's call it N. So this N, so this mimics a vector under the global SO3 rotation. Let's just do the usual 5-4 theory on this guy.
They still have this monopole there?
Oh yeah, no. For now, let's ignore the monopole. They are irrelevant anyway. I think the large N calculation is saying they are even more irrelevant at the critical.
Sometimes when you break the symmetry,
Oh yeah. They will come back, but that's what I will get to at some point later. Yeah. And this order parameter couple to the to my fermion as a mass. Specifically, it couples to the spin degree of freedom alpha beta alpha v beta v. So this valley index doesn't see it, but the spin index sees the my coupling as a right. Yeah. The point is, I'm now trying to drive. Oh, I've erased it. I'm now trying to drive this Dirac spin liquid to this 120-degree magnetic order. Right? So to spontaneously break that order, the simplest theory you write down, which turns out will work, is to drive a Landau-like transition. But it turns out for this one, you want to drive, well, because the fermions form spinors under the SO3, if you want to gap it out with a Dirac mass, the highest you can go to is just spin 1 of the SO3. So it's a vector. That's.
Are you saying that at the transition point from DSL to this order, you have this new anti-Dirac inversion?
Yes. So if you tune that to the critical point, that will be, the claim is that's this. So that's yes. Well, it's multi-critical, but it's critical in the sense that there's only one tuning parameter you need. Yeah. So the claim is, of course, if R is larger than RC, N is gapped, so you integrate it out, it's just your QED gauge theory, nothing much to say about it. So let me just focus on if R is smaller than RC. So okay, let's just say up to a basis change, you are in the z direction. You condense in the third direction. Sorry. Right. It's just a basis choice. So what does that mean? Well, if you plug this expectation into that mass coupling, it's telling you that your Dirac fermion gets a mass, which is not surprising given the form of the coupling, but it gets a mass of a specific form. That's essentially a mass that's opposite for spin up and spin down. I'm just picking up a sign randomly here, but for my later convenience. Right? So the valley index, there's nothing there, but the spin up and spin down gets opposite mass. Oh, sorry. I should have mentioned, since this is a vector, this condensate already breaks spin rotation SO3 symmetry, but it only breaks it down to SO2. Right, so we're not done yet. This SZ rotation, this is generated by the SZ. Right, that's not broken. Okay. But now let's continue. The Dirac fermion gets this type of mass. So the Dirac fermion are gapped. So if I go to energy scale below the mass scale, or there are the Goldstone this n vector, but they don't do anything particularly interesting. So in the IR, let me focus on only the Maxwell photon theory. So described by this A mu. So its action is just the Maxwell action. There's nothing fancy about it. But let's now ask what happens to the monopole. Right? So if I have a Maxwell photon theory, the monopole is unique. There are no 6 monopoles forming some funny representation of SU4. And that's natural because SU4 is now broken. Right? So I don't have this 6-fold degeneracy on the monopole. So this degeneracy on monopole lifted. And you can see that from this state operator correspondence, because the original monopole, there's a degeneracy because I have 4 zero modes, I can fill 2 of them, but any way of filling them up is energetically equivalent. But no longer so when I have this mass. So this mass is telling me that when I fill the 0 modes, well, the 0 modes are no longer at 0 actually. This guy, the spin up guys, have negative energy, and the spin down guys have positive energy. So the only monopole that's left, remember I have to fill 2 of them and anti-symmetrize. The only monopole that can ever be there is both the spin up monopole, sorry, the spin up 0 modes filled for both values. Right, so this is the unique monopole, and in particular, in the Maxwell theory, remember the monopole is spontaneously condensed. So this is a theory where this guy is condensed. But now, if I look at the SZ charge, this the unbroken SO2 charge, this guy carries charge 1, right? It's 2 spin up. So this guy carries SZ equal to 1. So now I have it SZ equal to, SO2 charge 1 operator that's also condensed. That means this SO2 generated by SZ is also spontaneously broken. So the upshot is that after this monopole condensate, my SO3 is now broken to nothing. Right, remember, this is very different from the square lattice case in the DQCP, where I condense my my spin-on boson, the SO3 is broken down to SO2. That's why you get the collinear pattern, this up, down. But in this Dirac-spin liquid case, the natural magnetic order you get is an order where no subgroup of the SO3 is capped. And that's what you have with this coplanar magnetic order. Remember, for the coplanar magnetic order on the triangle, you have some spin pointing here, some spin pointing there. There is no subgroup of SO3 you can find that leaves this pattern invariant. Of course, there's the lattice aspect. There's how they go from, when you go from one lattice point to the other, exactly you rotate by 120. That's a more complicated question. It has been answered, but the way to see that is more complicated. So I'm not going to explain that here. Yes?
Why do you think it's coplanar? Why cannot it be the out of plane?
Oh, sorry. So here the definition of coplanar is that, yeah, I didn't mention this, is that the SO3 is completely broken, but there is a time reversal combined with spin rotation that's kept. So, yeah, essentially you can do it. Let's say imagine these are pointing in the SX, SY plane. You can do a pi rotation by SZ and then do a time reversal, and then they'll flip back. If it's canted, you lose that symmetry. So it turns out for this case, you do have that time reversal. So it's coplanar, it's properly coplanar. Yeah, yeah, that's some subtlety I didn't explain. Yeah. Yeah.
So did you use here the fact that you're on triangular lattice and that you had this charge 6 monopoles microscopically? You had this argument that on the triangular lattice, the action was perturbed by charge 6 monopoles.
The charge 3, like
Charge
6 pi.
3, yeah,
Yeah.
charge 3. So did this play a role in your argument?
Yeah, for this argument, it doesn't matter because the charge 3 monopole has nothing to do with this guy. So because this carries spin, when they carry U1 charge, there's no monopole you can put in. Right, because charge 3 monopole will carry charge 3, will carry SZ charge 3, and you don't want to put that in. So the charge 3 monopole that you put in here is some other order parameter that has to do with lattice symmetry. So in this picture, they don't do anything. Yeah, they will do something if instead of choosing to break spin rotation symmetry, you choose to break lattice symmetry. There, turns out what happens is this sigma matrix no longer act on the spin index, but they act on this valley index. And there you have the monopoles. It turns out you'll get a gap, but the Maxwell photon will no longer stay gapless because they are this three-fold monopoles, and then they gap out the theory. You get something that looks like VBS, the valence bond solid, but it's a more complicated valence bond solid.
Why did the photon stay massless if you had this monopole?
Sorry, are you talking about this case or the okay, the previous one, the photon does stay gapless. They are just the Goldstone mode of this spontaneously broken SZ symmetry. Right? So if you look at this symmetry breaking pattern, there are two Goldstone modes. It turns out one of the Goldstone modes come from here. Three. Two of the Goldstone modes come from here, and the other one come from this monopole. This free photon left. Yeah.
Why can't they just argue, turbulence I integrated about, the massive, I have this photon AU.
Yes.
It's in presence of monopoles.
Yeah.
So I have Polyakov mechanism.
No. The monopoles are not added to the action. No. Yeah. So those are heavy monopoles. Those after you have this gap, they are not the monopole in the microscopic. In the Maxwell theory, they're more they are actually this monopole dressed with some gapped fermion. Actually, fermion bilinears. They are like this monopole, but then dressed with some of the other fermions that are already gapped. So they do not. Essentially, they become irrelevant because they're dressed by the gapped object, and they don't give you the Polyakov mechanism. Yeah. Yeah. If you break symmetry in the valley space, that will be what you describe. Yeah, that will gap out the ground state. All right. So I think that's more or less what I've prepared, and I think this is a good place to stop. Thanks.
Any other question? Okay, if not, then let's thank Chong for the very nice series of lecture.